For some of that time, it's dark, and for the rest of the time, it's light. Day and night are easily explained by the fact that the Earth spins on its axis as it orbits the Sun. But what happens in the Arctic shows that things aren't quite so simple. Because here in the summertime, there is only day. The sun never sets at all. And it never sets because of something that happened to our planet 4.5 billion years ago. When our solar system began, it was a crowded and dangerous place. Earth was just one of thousands of new planets orbiting the young sun. And it was on a collision course with another smaller planet called Theia. Theia was totally destroyed. The debris from the crash eventually formed our moon. Earth survived, but the crash had changed it forever. Theia knocked the Earth over. Our planet spins around its axis at an angle of 23 degrees away from the upright. This 23-degree tilt means that as Earth orbits the Sun, different parts of it get more or less exposure to the Sun. In June and July, the tilt means that the northern hemisphere is facing towards the Sun. It's summertime. But in the south, the opposite is true. The southern hemisphere is getting far less sunlight. It's the southern winter. Come December and January, the Earth is on the opposite side of the Sun, so the tilt means it's winter in the north and summer in the south. At the poles, the Sun never sets in summer and never rises in winter. But it's not just at the extreme ends of the planet that the tilt is significant. For the rest of us in between, the length of our days changes through the year because of Earth's tilt. Tilt brings us spring, summer, winter and fall. Without it, there would be no seasons. As the seasons change up and down the surface of the Earth, they bring on dramatic and spectacular events. From the intense storms of Tornado Alley.
We're watching some very strong rotation here. This purple area here is winds about 150 kilometers towards the radar.
To the dramatic spring breakup of ice on frozen rivers.
I've been watching it for 62 years. You're going to be faced with high water and a river full of ice. You got nothing out of that except a flood.
It doesn't take much to work out that the temple has something to do with the year. There are 4 sides which represent the 4 seasons. Each has 91 steps. These, combined with the top platform, make a total of 365, one for every day of the year. But the temple is more than an ancient stone calendar. It also records the solstices, the shortest and longest days of the year, the extremes of the Earth's tilt relative to the Sun. And it records the spring and fall equinoxes, when for a moment there is no tilt relative to the Sun. Today is the spring equinox, a point in the year when day and night are of equal duration. The The crowds at Chichen Itza are waiting for a magical transformation, which only happens here on the day of the equinox. As the afternoon sun aligns with the pyramid, it casts a shadow along the edge of this staircase. As it develops, the shadow provides the carved snake's head at the bottom of the steps with a body. This is Kukulkan, a heavenly serpent, the divine messenger of the Mayan sun god. The ancient Mayans realized that the equinox was a significant point in the year and understood enough about the seasons to capture this moment in stone. But they didn't know why it was significant. They didn't know that this is the point in its orbit at which the Earth's tilt is irrelevant. Because its axis is momentarily at right angles to the Sun, neither pole is tipped towards it, and so everywhere on Earth receives the same amount of night and day. From this day forward, the Earth's 23-degree tilt will reassert itself. As the northern hemisphere tilts more and more towards the Sun, the days become longer and warmer. Unsurprisingly, this turning point has been traditionally marked as a time of renewal. From the pagan dawn ceremony at Stonehenge to the burning of the Wicker Man in Northern Ireland, and the Catholic Fiesta de las Fallas in Valencia, Spain. As the northern hemisphere tilts further towards the Sun, the extra heat and light have a dramatic effect on animals and plants. Thunderstorms can also give birth to a phenomenon called a haboob, like this one in Phoenix, Arizona. These massive dust storms occur in arid regions where the leading edge of a thunderstorm collapses, generating a super-fast downdraft. The falling winds kick up a wall of dust and sand in front of it. As summer progresses, the planet's tilt pushes the northern hemisphere even further towards the Sun. This brings even more solar energy to the warming lands and generates the biggest single weather event on the planet. Oceanographer Helen Chersky has come to Kerala on India's southern coast to witness the start of the monsoon.
We're on the edge of the land, big Indian landmasses behind me, the oceans to the south, and this is where the monsoon is set up. What's driving the monsoon is the difference between the land and the sea. So the sun is beating down on this area of land, especially at this time of year when the sun's almost directly overhead. And the land heats up very, very quickly, whereas the ocean heats up much more slowly. If you look at the sand here, the surface that's being heated by the sun is hot. And if you dig down, you don't have to dig down very far. Even a little way down, that sand's really cool, whereas this layer here is really, really hot. And so you can see that only a thin layer is being heated. So all of that sun's energy that's being absorbed is going into this really thin layer, so it heats up very, very quickly.
So, the sun heats the land dramatically, but not the ocean. Here, the Indian Ocean is much cooler than the land. The reason is, the ocean requires much more of the sun's energy to heat it up.
The ocean is also relatively cool because to heat the surface, you have to heat much more than just a thin layer. What happens is that winds that blow across the surface of the ocean generate turbulence which mixes that top layer. So as soon as some water's been heated at the top, it gets mixed down below.
As we enter summer, the land heats up fast, while the ocean lags further and further behind. Now the air above the land becomes much hotter than the air above the ocean. As the warmer air mass rises above the Indian subcontinent, it creates a kind of vacuum behind it. This draws in the cooler, denser air from the ocean to replace it. Because of India's particular geography, the process happens on a huge scale. It's a triangular peninsula with both wide, hot plains and, crucially, a very long coastline. This combination sets up a powerful and sustained movement of cooler ocean air towards land, called the monsoon wind. But what we think of with monsoons is not wind, but rain.
Enormous cloud overhead, enormous black cloud, which is built 15 kilometres up into the troposphere, and the first drops of rain are just starting to come down.
As the sun beats down on the ocean, some of the water evaporates and is carried up into the atmosphere where it forms vast rain clouds. To capture their formation, Helen has set up a series of time-lapse cameras. The monsoon winds drive the moisture-laden clouds across the land, bringing with them a torrential downpour. 80% of all India's rains arrive in this seasonal deluge.
This is the monsoon. This is all the water that's been lifted up off the ocean in the past few days because of the heat that's been carried inland, and it's now falling on top of me. The raindrops here are really, really large, and you can see they're making pot marks in the sand because they're so big. And the reason for that is that in warm conditions like this, up in the clouds, the drops are joining together to make bigger drops. The smaller drops actually stay up in the clouds because they're being lifted out of the way, and all that falls are these massive drops that are covering me now.
The models have linked these higher temperatures with changes to the Earth's angle of tilt. Today, the angle of tilt is 23.4 degrees. But every 41,000 years, that angle swings between 22 and 24.5 degrees. Back when the Sahara was green, the Earth was close to its maximum tilt of 24.5 degrees. It may seem like a tiny shift, but combined with small cyclical changes in the direction of the tilt and the shape of our orbit, the result was the sun shone more intensely over the northern hemisphere, and it powered a Saharan monsoon. Then, 5,500 years ago, the cycles changed. The Earth's tilt decreased again, moving closer to what it is now. The Saharan monsoon stopped, and very quickly, the water and vegetation started to disappear. The green savanna was transformed, leaving what we see today, one of the world's largest deserts. Recent research suggests that the Saharan monsoons may have had an even greater impact on human civilization. Old lake sediments suggest there was another wet phase in the Sahara's history, 120,000 years ago.
This particular Green Saharan episode is a really exciting one because it may well have controlled the migration of humans out of Africa.
Modern humans evolved in Africa around 200,000 years ago. But how they migrated through the impassable Sahara Desert and out of Africa has long been a mystery. The Green Sahara of 120,000 years ago may provide the answer.
It's at this time where we find the first evidence of modern humans to the north of the Sahara, along the Mediterranean coast. Presumably, these humans got across that Green Sahara at that time. And once they're up across the Sahara along the Mediterranean coast, it's easy for them to just migrate out through the Levant and then into Europe, which they did about 50,000 years ago.
It's remarkable to think that tiny variations in the Earth's tilt may have led to one of the most fundamental movements in human history.